Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our C programming language series. In this lesson, I'm going to be talking about some fundamental operations found in the string standard library in C. These are things like memset, memcompare, memmove, and strcpy. Now, let's go ahead and dive in, and let me show you where to find these functions so that you can start using them in your C programs. So, the very first thing I'm going to do is actually look at the manual page for something called string here. And what you're going to find here is that this is a list of functions, bcompare, bcopy, b0, and then some of the ones that I mentioned that we're going to learn about today, things like memcpy, memmove, memset, etc. And you're going to find that they're actually found in the string.h file. Now, I don't know this for sure, but string stands for byte string. And if you think about what a byte is, just 8 bits of information and a string of them, that's like a block of memory. So that's why I suspect that these are found in the string.h library and not memory.h or something else, but just wanted to give you that as a tool to remember. And the other thing that I'll go ahead and show you is that some of these operations, things like bcopy, we now use memcpy instead. So that's what I'm going to show you, the latest and greatest stuff that we want to be aware of. All right, with that said, let me go ahead and show you just an example program, and then we'll go ahead and take a look at how to use some of these functions. So what I've got here in this program from our main here is I'm going to create an array on the stack here with 27 characters. And again, you can assume 27 characters here on our architecture is just 1 byte per character. Okay, so again, we're going to want to think about things in terms of bytes, especially as a C programmer, in order to use these functions. And then what I'm going to do is just go ahead and initialize the actual data here in my array here, starting from 65 and adding to these index from 0 all the way up to plus 26. And at the very end of my character array here, I'm going to go ahead and put a null character here. Okay, so let's go ahead and see why did I choose this particular number of 65. And if I move the adds out here and go ahead and just check this out on our ASCII table, recall that 65 is the decimal value for capital A here. I'll zoom in a little bit so you can see. Hopefully we don't get any more pop-ups here. But there we can see decimal 65, the letter A. And later on, we might change this to 97 or do something. So that's why I'll be doing those things later in the lesson. So I'll go ahead and close that out. And let's go ahead and run this program. I'm going to go ahead and compile with debugging symbols here, warnings, treat those warnings as errors, which would be good practice, add our program, and output this as prog. And there you can see it on one line. And let's go ahead and just run this. And we can see the alphabet that's printed out here. So this is the fundamental program that we're going to go ahead and start working on. But let's go ahead and now that we have this data here, we can start playing around with it. And you'll notice that I've also given myself a node here, and we've seen some of this in sort of linked lists or if you've implemented this. And really quickly, what I might want to do here, just to show you some of these operations, and let's go ahead and just indent this to make it look a little bit nicer here. Let's just go ahead and print off the size of node t here. And I'll go ahead and let's go ahead and use %lu here and an end line and size of node t, just so we can go ahead and, again, because we're going to want to think about things in terms of bytes, see that this is indeed 16 bytes here. Looks like it gave us 4 here, maybe additional 4 bytes of padding, and then 8 bytes for the pointer. That would be my guess of the layout. And if you want to go ahead and refresh on why exactly this is printing out 16 instead of maybe 12 or some other value here for the size of, then go ahead and watch some of the previous lessons in this series and subscribe, etc., etc. All right, so with that said, let's go ahead and start looking at some of these memory functions that we want to be familiar with. Okay, so the first one I want to go ahead and show you is memset here. And basically what memset does is it sets a block of memory. Okay, so let's go ahead and just do this as an example. And let's go ahead and do it with our alphabet example to start here. Let's say I didn't print out this data here, okay? Or rather, I didn't set this data in this array. So let's go ahead and run this program here. It compiles, and I run it, and clearly you can see that there's something in here. In fact, we just got garbage. And I'm actually going to run this a few times, and you can see that we're getting different values inside of our memory here. So typically we always want to initialize our memory to some default value or the actual value that we're going to put in place. So in this case, we were able to set it to 65 here. But if I want, I could actually go ahead and I'll comment out this entire loop here, use the memset function to initialize all of our memory here. So let's go ahead and take a look at what memset is in our manual page and look at this. So memset. And how most of these functions are going to look is you're going to have S, which is the source, and that's going to be your input. So it'll usually be abbreviated as S or src. C is going to be the character that we want to fill. And most of these functions, you'll just see N, which is usually the number of bytes that we want to perform this operation on. So let's go ahead and just play with this memset operation a little bit just to understand what's going on here. So with memset, the input is actually going to be data. And the value, the integer that I want to set here, let's go ahead and set it to 65. And how about 26? So the first 26 bytes here will be set here. So let's go ahead and, again, play around with this. So I'm going to go ahead and recompile this, rerun this, and now you can see everything is just A all the way here. So it sounds like our program is screaming, which sometimes they do. But we'll go ahead and leave it at that. Now let me go ahead and just again show you how memset is working. Let's go ahead and again initialize our alphabet. So I'll comment out memset, and we'll go ahead and recompile this. I'll rerun it, and you can see that we have our alphabet. But now let's go ahead and use memset, and let's just set the first 13 characters to A here. So again, the pointer that I am setting here, which, well, our array is being treated as a pointer here to this block of memory, it should just set the first 13 characters to A. So you can see how it's initializing those. Okay, so let's go ahead and compile this. Let's go ahead and run it. And we can go ahead and see the first 13 characters set as A here. So it seems to be working fantastic. And this is a nice way to communicate exactly what we want here, setting this block of memory. And we can use all the different tricks that we've learned about previously. For example, let's go ahead and use some of our pointer arithmetic. So I'm going to go ahead and offset this by 4 characters in this case, because data is a character pointer. And we'll go ahead and compile it. I'll go ahead and run. And you can see we have A, B, C, D. And then at this point, we go ahead and offset and set our next 13 characters, or rather overwrite them with the letter A. And then we have the rest of our alphabet here. Okay, so I think you kind of get the picture of what memset's doing. It's a quick way to initialize some memory. And I want to go ahead and show you the same trick as where you might pragmatically use this. Many times I will use this to sort of zero initialize memory, but this can also be useful for our structs too, for instance, because oftentimes what you'll do in your code is you'll have something like this and say, hey, let's create a node T, my node, and then you'll say something like my node.data equals 0, my node.next equals 0, or rather null. And let's go ahead and just compile this here. Oops, got to get rid of line 31. And, well, I guess we're not actually using this value here. Let's go ahead and just print off my node here. Printf my node.data. So we got to do the same thing. And I'll go ahead and print out the integer, my node.data. And let's just go ahead and print off the next field as well. And let's go ahead and make sure that since this is a pointer type, we treat it as %p. And I'll recompile this. And of course, I've got to make sure that I spell everything right here. Capital N and capital N here for our node so that I actually can find it. And now I run this, and we can see that it is essentially 0 initialized here. Okay. Now, if I didn't do this initialization here, which let's go ahead and just get rid of these values, let's go ahead and see if we get the same garbage result here. And in fact, we're getting enough warnings here. So I've got to get rid of my warnings as errors. I'm going to leave them as warnings just so you can see that this is a bad thing to do in our actual program. And I'll run it. And again, we can see that we're just getting essentially garbage here. So if you really do want to sort of zero initialize things in your struct, you could, again, use memset. So memset, we want to pass in, well, the address, my node, how many bytes that we want to modify. Let me go ahead and leave memset here so you can go ahead and see, or rather the character here, 0. And then, well, how many characters we want to modify? Well, that's going to be the size of our node T. We want to zero initialize everything here. Okay. So now let's go ahead and try to recompile this, rerun, and now you can go ahead and see that we have 0 initialized our struct. So just like blocks of memory, like array, this works, but this also works the same for structs. Again, we're sort of thinking about everything in terms of memory here. And just to make that concrete, I think it's been useful, or folks have mentioned that it's useful to actually see these types of structures here. So just to recap here, what we're doing with memset is I have this struct here, and it has two fields here, data and next. Although I do want to sort of clearly illustrate what my compiler is doing here, is it's doing data here, which is 4 bytes. I think there's a little bit of padding here, 4 bytes that it's inserted. And then we have 8 bytes for our next pointer. And then when we use memset, we are essentially just zeroing out everything here. So there's just zeros all in our field. And in fact, this is doing this at a byte level. So to draw 4 zeros isn't quite accurate. I should be drawing 4 zeros per each of the fields in our struct here. And there's 8 at the bottom here. Okay, just so we get an idea again of what is going on with this particular example of memset. Now, of course, I could set this to any value that I want, and that's also totally fine here. All right, so I think we understand memset. Let me go ahead and comment this out for now. And then let's go ahead and look at some other examples here for what we can do here. All right, so that's memset, setting a block of memory. Now I'm going to use something called memcpy, which is how we can copy a block of memory. So let's go ahead and look at the manual page for this, memcpy, and it copies a memory area. So from some source to some destination, and then the number of bytes that we want to copy here. Okay, so again, looking like a rather similar form here. Now it's important to actually read the descriptions here, and they're short, just a few sentences here. But there is a little caveat here saying, importantly, and I'll put this just so it's on one line here, that the memory areas must not overlap here. Okay, so if I'm trying to copy some block of memory into another one, it's important that I'm not copying into myself. So again, let me go ahead and just illustrate what I mean here for memcpy. Basically, this usually involves that I have some allocated data here and another region allocated here of memory. And I want to copy the contents, rather, I should say, from this source into the destination. Okay, and that's where I get my new copy. Now, of course, this region doesn't have to be the same size, but this is specified by memcpy's arguments. And again, this is the destination, or D, source, src, and then the number of bytes that I want to copy. It might just be a region, say, from here, for instance, into this memory, and then this remains garbage or whatever. But let's go ahead and play around with this just a little bit here, just so we can see how memcpy is working. Okay, so we'll go ahead and keep working with our alphabet example here. And let's go ahead and first, again, just do a complete copy. Okay, now, usually this operation, again, you could imagine doing this sort of one item at a time here. So let's go ahead and I'll comment out memset here. And we need a destination here. So I'm going to just go ahead and call this destination. And for now, I'm just going to make sure it's the same size. That makes things just a little bit easier for us to work with here. So we've set up all of our data here. We'll print off our data. And let's go ahead and just call this destination, which is really copy. That could be another thing that we call it here. But let's go ahead and set up this problem here. And let's go ahead and work with memcpy. Okay, copying the memory area. Okay, so let's go ahead and do this. Memcpy, our destination is dst. That's an array here, so we know what the address is. Our source is going to be the data. And then the number of bytes that we want to copy, well, their size, 27. Okay, so if this is working, we should see a complete copy here, the alphabet printed out twice. Okay, so let's go ahead and compile. Let's go ahead and run. And we can see, looks like everything's working just fine here. So perfect. This is exactly how memcpy works. Now let's go ahead and again, play with this just a little bit here. For instance, and this is the way to learn this, let's say our destination is just 13, for instance. So our actual region that we're copying into is smaller. Well, let's go ahead and just reduce the number of bytes to 13 here. And we'll go ahead and copy this. And we get something that's really interesting that's happening. And go ahead and see if you can try to pick out what's actually going on here. But when we're going from our data here into our destination, again, our destination is smaller. It should only be the first 13 characters or the first half of the alphabet here. But for some reason, it keeps on printing here. Well, I can actually show you exactly where here. our 13th characters without having to count them out, because what happens is you see that we have the repeats here of our actual data. Now I want you to think about this example for just a little bit here, and let's go ahead and see what happens here in this example. And let's go ahead and illustrate this down here. So I have data, and then I have my destination, which is A through Z here, and the null terminating character. And then I have my destination, right, where we're going to pass in the first 13 bytes, but that's only taking A through M here. And then I don't have any null terminating character. And in fact, since this is on a stack, the next piece of memory, which is going to be the thing that was allocated previously to that, which is data, is then going to print out. So in fact, when I'm printing out, just be aware here that whenever we print out strings in C, we need a null terminating character. So again, that's why at the end of my data, I put that null terminating character here. So again, let's just go ahead and do destination at 12. So that would be the 13th character. I'm just going to go ahead and manually set this to the null character so we could fix this example. And we could go ahead and see the fix here that is working this time. Last time it took us through M, which was 13 characters. Here it takes us to 12 characters and the null terminator. Okay, so that's what we're doing with memcpy. Now, this is something that we're going to commonly be doing, or you might commonly find yourself doing, copying strings of information, because these just happen to be characters. Again, we can do the same thing with a node if we want, and that's actually a great exercise for you to do, is to actually make a copy of this node so you can make duplicates without, again, maybe you have a template or some fields set already. But I do want to go ahead and digress just a little bit and show you another related function here called strcpy. And let's just go ahead and, in order to do this, I'm going to open up another terminal window here. And on the left side, I'm going to show you strcpy. And on the right side here, let's go ahead and bring up memcpy. And let's go ahead and get everything up here. And string copy, let's just go ahead and take a look at the arguments here, which just take a source to a destination, okay? And memcpy on the right side takes a source, destination, and the number of bytes. Now, the difference with this version of string copy here is that it'll just copy until it finds a null terminator. Okay, so I hope folks can kind of understand the difference or know how that works here. Okay, so it just copies a string. Again, almost the same rules, but it's just going to copy from some source into a destination until it finds the actual null terminator. Now, you can imagine, as we had in that example, that this can be dangerous if we're working with string data, for instance. And there is a safer version, strncpy, which allows you to specify the number of bytes. So I would recommend this, but again, just be aware of what the difference is between memcpy, which is just any amount of bytes, and strcpy. Okay, so I hope that makes sense. I'm going to go ahead and do an example with strcpy just to show you how this works. So let me go ahead and just change this example a little bit. I'm going to go ahead and put our destination back up to 27 bytes here. And then what I'm going to go ahead and do is, instead of memcpy, if I know I'm working with a string and I know it's null terminated, again, I can just use strcpy. And again, getting the arguments right, usually the destination first and data as the source. Let's go ahead and recompile this program. I'll rerun it and it'll work. Okay. And again, we do have to be a little bit careful with strcpy to make sure that our destination is big enough here until we run into that null terminator. Okay, so I hope that makes sense, and that's the difference with strcpy. So I do actually want to take a moment here just to show you memcpy with the struct. I think that actually will be useful for you to see here. I don't like to leave things hanging too much. And we've already done most of the work here because we have our node here. I've initialized it. And let me initialize it to some value like 7 here, just so we can go ahead and see that we have a some value here. And I'll get rid of memset here. And let's just go ahead and create another node, node t, my node 2. And I'm going to go ahead and set my node 2 without setting the actual data, but using memcpy. Memcpy destination is going to be my node 2 from my node. And since we want a complete copy of these, it's going to be the size of one single node. And let's go ahead and print out my node 2 and my node 2.next. And just taking a moment here to get our arguments all set. And that should do it for this example. Let's go ahead and, oops, looks like a few more things to fix up here. And the errors that I'm getting is because, well, we need to pass in an address here because memcpy is taking in a pointer. And let me just comment out this, all the other stuff we have here, just so you can go ahead and focus on only the code that's running. And let's go ahead and fix that up by passing in our address here of our destination, which is where we want to make the copy, and where we're making the copy from, my node. All right, so now we should be in good shape. And now if I run this, we can see that we've made a copy of these structs here, and they each have the same data and the same pointer here. So then this can be very useful if you have various design patterns or, again, are making a copy from one node to the other. All right, so let me go ahead, and now that I've done this here, I'll comment this out so I can share this code later, perhaps with folks if they're interested. And let's go ahead and look at this last example here, memmove, okay? And what I want to go ahead and show you is that memmove is very similar to memcpy, except it allows you to actually overlap regions of memory. So let's go ahead and demonstrate this. So let me go ahead to the manual page here for memmove and show you that this function copies, again, n bytes from source to destination, but the memory areas may actually overlap. Okay, so this is sort of interesting how it works. It essentially creates a intermediate buffer that we can copy into. So it'll look something like this, memmove, where I can create some region of memory like this, and then my destination, it could be the same actual buffer, and I could sort of rotate or move data from one section into another. So let's just go ahead and kind of play around with memmove a little bit here. Or you can think of it as moving it to a totally different buffer of the same size. So it can effectively do the same thing as what memcpy can do, but it's a little bit safer to use because it's making a copy in between. Okay, so let's just go ahead and play around with it and see what kind of results we can get here. I think this is a fun one to play around with the alphabet in particular. So again, let's go ahead and uncomment out this stuff here for our alphabet example. And I'll go ahead and leave in destination there. And I'm going to go ahead and leave in this memcpy here, like we did before. I'll get rid of memset because that gives us the two alphabets that we can play around with. So right now that they're both printing here, or at least the first 13 characters, until I find the null terminating character here. Or rather, this time we just got lucky. This happened to be garbage in here. So let's go ahead and make the full copy, all 27 bytes. All right, there we are. Okay, now let's go ahead and try playing around with memmove here. And again, just to look at this, memmove. And again, this name's kind of weird. It might throw folks off a little bit because it's move rather than memcpy. Because it's allowed to have the overlapping regions. Let's go ahead and leave this here. Destination, let's go ahead and say data. And let's go ahead and make data also the source. But I'm going to go ahead and just take the last 13 characters. And I want to go ahead and overlap them. Or maybe let's just say 12 characters. So this is effectively going to insert part of the alphabet from the source, the backside, and put it to the front here. Okay, so let's go ahead and run this just so you can kind of see how this works here. And you can go ahead and see that basically we chose M and O P, etc. in our alphabet, and we're able to say, hey, you know, take this last half here that started at M and O P all the way through X here, so 12 characters, and just insert it at the front here. And this could be a way that you can sort of rotate data, which is kind of interesting. Now, this could be a fun example to actually, or an exercise to put this in a loop here, where you just sort of rotate by one, and you can actually see the alphabet rotating, for instance. But that's the idea of memmove. And as I mentioned, we can also use this like memcpy. So I'll go ahead and get rid of memcpy here. Let's choose our source as data, and then our destination, and then go ahead and put in the 27 characters here. Recompile, and we'll go ahead and see that we get the same result as before. All right, folks, so I hope that was useful. I hope you got to see some of these operations like strcpy, memcpy, memset, and memmove, of course, which are commonly used operations in C as well as in C++, in other languages, D, Rust, etc. We're going to be doing memory operations. And again, it's important to understand what the limitations of these functions are. They're relatively simple, but you just have to think about things in terms of bytes. So with that said, folks, thanks for your time today. I hope you subscribe so you won't miss other lessons. If you do have questions about this specific lesson, though, feel free to comment below, give it a like if you enjoyed this lesson. And with that said, I'll look forward to seeing you in the next lesson.